Let's wait for 2 3 minutes. After that, I will start. Okay, let's start. So this is the sixth week, problem solving session on advanced atmospheric physics. So the today's plan is again to look at the assignment 5 question. Although I think people have got the solutions of assignment 5, just a little bit of discussion I will do, and we can move forward to the week 6 contents. So assignment 5 question is number 1, which we will just try to discuss a little bit because the solutions already you have. Second is we will try to see some basic concepts which are required to understand the internal gravity waves. It's a long derivation of internal gravity waves, but what I have seen from the assignment 6 questions, these are based on these fundamental concepts, which we will apply to derive these internal gravity waves, not particularly on the internal gravity waves. Okay, so we will see the internal gravity waves definitely, but we will try to understand these basic concepts or certain formulations, how we can derive those formulations, and that will be mostly useful in assignment 6. Okay, so we will look into these couple of things, and finally, the pressure as the vertical coordinate is being introduced in the week 6 content. So we will see if time permits. Okay, pressure as vertical coordinate. Right now, till now, we have done the vertical coordinate as some height z, but we will see that the pressure coordinate can be also used as a vertical coordinate. Okay, and how we can convert this x, y, z, t, that is x, y is always there, time is also there, but z, the fourth dimension, that is fourth dimension or the third dimension of space, x, y, z, that z direction, that how can we change into x, y, p, t, that is the p is the pressure coordinate. Okay, so this we will see. These three are the basic plans for today, and then we can see whether we have, particularly the third one, whether we can do it or not. Okay, so let me turn off the camera. Okay, okay. So first we will look at the assignment five questions. Just little bit of discussions, will not go much of details. So if you see the first question, uh, it shows that, or it asks, shallow water gravity waves. There are four options. Generally observed near the certain discontinuity in the medium, which is true, right? We have seen that gravity waves, the shallow water gravity waves, occurs where there is a density gradient. Rho one, rho two, we have seen, we have derived it. So this is fine. There is a certain discontinuity in the medium. So this is true. The wavelength is much larger than the depth of the fluid. So we have seen that lambda by h last at very last of the last uh, problem solving session. I have written it down for what is the difference between a deep water gravity wave and a shallow water gravity wave. And we have seen that for a shallow water gravity wave, the lambda is much, much greater than the h, the depth of the fluid. So that is also true. Third, the restoring force is gravity itself, of course, because it's a gravity wave, density discontinuity is there, so the restoring force is gravity. We have discussed this, all these options, and hence this shallow water gravity waves satisfies these three options. So all of the above is the correct option. Okay. Next is the second question. Very simple, based on the phase speed of the gravity waves. Imagine a fluid system having depth 9.2 kilometers. What should be the speed of the surface gravity wave for such a system on the Earth? Simple. So this is an imaginary question where it is being given that the fluid system has 9.2 kilometers of depth. What should be the speed of the surface gravity waves? Simple. C is equal to root over gh. So we can just write here. So this is assignment 5. 5 question discussion. Okay. So the first one was that the shallow water gravity wave. I'll just gravity wave just quickly. So we have seen that this already, that in the last problem solving session, that there is a density discontinuity, rho one, rho two. So sudden density discontinuity exists continuity. And we know that the wavelength lambda is much, much greater than the depth. This we have already seen. And gravity is the restoring force. This we have already discussed. So, second is that it has been asked that the your H depth of the fluid is about 9.2 kilometers, right? So, what is the phase speed or the of the surface gravity waves? It's just root gh. You don't need to worry about u bar and all those things. You can assume that to be zero. Okay, so this becomes 9.81 into 9.2 into 1000 because we have to convert it into meters. Okay, so if you just do it, if you just calculate it, it will come out near 300. Uh, yes, 300 meter per second. Okay, just simple calculation, so it will come out to be roughly near 300 meter per second. Okay, fine. The third one, let's see what is the third question. What could be the typical vertical movement of air at the equator in the troposphere during equinoxes? Okay. So what is the meaning of equinox? What is the meaning of equinox? Equinox is when the position of the sun is directly over the equator. Okay, directly over the equator. This is when you are on the earth and you are seeing the movement of the sun. So earth is now your reference frame and you are seeing the sun's movement. Okay, so this is now when this is your earth, suppose. Okay, so this is your earth, and there is a tilt of the earth, of course. So when the sun is direct radiation falls over the equator. Okay, that is the equinox time. And when we call this as the equinox, it's roughly near 23rd or 21st of March. Okay, and some 23rd of September. Okay. So these are the 20. So it's a, I would say, a range about 21st to 23rd. Okay, so these are the two times when sun's direct radiation falls over the equator. Okay, so what happens is that, so if you have an earth like this, you have equator here. Okay, there is a tropic of Cancer, tropic of Cancer at the northern hemisphere, and there is a tropic of Capricorn at the southern hemisphere. Okay, so this is south, this is north, this is actually 23.5 degrees, this is also 23.5 degrees. South, this is north. Okay, when sun is directly over here, this is called the solstice, the summer solstice. Okay, so this happens on the 21st June. This is the winter solstice, which is 21st of December. And so sun generally travels to the northern hemisphere and again comes back. So when it goes to the northern hemisphere and comes back, it comes twice over the equator. So those are the equinoxes. This is called, the March one is called the vernal equinox, and the September is called the autumnal equinox. Okay, so too many things are there, so you don't need to go into the details right now. But thing is that during the equinoxes, sun is over the equator. As you can see, when the sun's direct radiation is over the equator, there is a chance that this equatorial region, equator warms, and because of the warming, a low pressure is created. Okay, low pressure is created, and low pressure regions generally has convergence. So this is the column near the equator. Okay, this is the equator. So winds generally converges, and when where it will go if it converges? It cannot go down, right? This is the surface, so it has to go up. So you will always have rising motion wherever you have the position of the sun. Generally, you have the rising motion. Okay, so this is the simple question. So it is a rising motion. Restoring force of Rossby waves. I don't know whether the Rossby waves are covered yet, but fine. If it is giving the Rossby waves, generally the rotation plays a key role. Okay, in the Rossby waves, gravity compressibility does not play any role. So Rossby waves, I have given an idea in the last professional session where I have shown the jet stream, and you can clearly see that it is shown. It can be seen over the mid latitude region where the rotation becomes much important. Okay, Earth's rotation. Right. So this is another restoring force for acoustic waves. We have seen that is the compressibility of the medium. Right. This we have seen already. Next, which of the following waves is or are dispersive in nature? Except for the shallow water gravity waves, all are dispersive in nature. We have seen the deep water gravity wave, they are dispersive in nature. But yes, Rossby waves we haven't seen, but it is dispersive in nature. I think while talking about dispersive waves, I have given an example of Rossby waves. So that is dispersive in nature. Okay. So only shallow water gravity waves, which we have seen in the last session, that it is not a dispersive wave. Same as the acoustic wave. This is an interesting question, which I have given some hint in the last session. A storm offshore generates waves. So we know, or you will be knowing, that whenever a cyclone forms over Bay of Bengal, uh, generally the fishermen near the coasts are being asked to vacate that area because there will be some strong waves can be seen near the coast. So whenever there is a deep storm, it creates the energy of the storm creates waves. Okay. So now it has been asked here, a storm offshore generates waves with a period of 20 seconds. So the time period is being given. If the storm is 100 kilometers offshore, the time for waves to reach the shore will be. Actually, if you see the waves, the energy of the waves, which creates most of the disturbances. So instead of focusing on the crest or trough of the waves, when the crest of the waves will reach, we should look at when the energy of these particular waves will reach the coast. Okay, and for energy, we generally look at the group velocity of the waves. So in this case, for the storm, we have to consider the deep water gravity waves, not the shallow water gravity waves, because shallow water gravity waves does not transport the energy through the group velocity. Okay, so here we will consider the deep water gravity waves, which I have which I have just uh, hinted in the last session. Okay, so simple is the solution that your storm generates generates gravity waves. Okay, and we will consider the energy of the we will consider when the energy of the waves reaches. Okay, not the crest and trough. Okay, so this energy is generally transported through group velocity. Actually, there is a nice derivation in atmospheric dynamics that how group velocity is related to energy. That is a very nice derivation. But sometimes, if I get some time in between, or if we have some extra session, we can discuss this. This is a very interesting thing. Okay, how the energy is transported through group velocity. We always say that group velocity through group the wave group, the energy gets transported. So how it is done, how it is mathematically related, that we can also see. But right now, let us focus on what we are doing. So we know that for the deep water gravity waves or simple gravity waves, if you do, that is G into K. We have seen in the last. Not it is not a shallow water gravity wave. It is in general gravity wave has this. Okay, shallow water has that approximation lambda much greater than h. So this is generally we are considering lambda much less than h. Some kind of a deep water place. So if you just differentiate with respect to k, you get this, right? So delta omega delta k is nothing but Cg, the group velocity, g by 2 omega. So omega is what? 2 pi by t. Time period of the wave is given. T is given as 20 seconds. So it will be 2 pi by 20 And you can calculate therefore the group velocity. So g by 2 into 2 pi by 20. So 2 it can be 10, this becomes 5, so it will be 5 g by 5. This is the group velocity. Now, how much time it will take to reach, I think 100 kilometer was there, the distance. Yes, 100 kilometers. So now it's quite simple. So Cg is equal to the distance is divided by the time which it will take. So T, the energy or the energy which is generated, how much time the wave energy required or the group of the waves will travel towards the coast. That's what we are trying to see. Okay, so this is 100 into 1000 definitely because in meters it will come, and this will be 5 into, you can say 9.81, or you can take 10 also, that's fine, into 5. So if you do all these calculations, this will come in seconds, remember. So in order to convert it to hours, you have to divide the this. So this will be in hours. So if you calculate, I think it will come out to be about roughly about 1.8 hours. Just check the calculation once. This should be okay. This is, I think, given in the assignment solution, so already known. Okay. So we will see the, actually here we are saying the group of waves or the packet of waves, how it is traveling. Waves traveling and reaching the coast. Okay, so this is what. Let's go to the next question. Generally, gravity waves are important in which part of the atmosphere? Actually, this is not yet covered. Okay, so we will see this where it is important. Actually, the answer should be stratosphere and mesosphere, but since one of the options we have to choose because it's not troposphere, it is generated in the troposphere, but the energy is transported much higher, higher altitudes. Okay, so it is actually mesosphere, which is the correct option. Okay, so that we have to see. Okay, so it generally affects the mesosphere the temperature profile. Okay, so fine. So these are the couple of questions in this assignment. Okay, so we can now look into the week 6 content. Okay, so in the beginning, I have seen assignment 6 questions, so many numerical questions. I will not solve so many numericals right now. I don't have numericals much right now. But what I will do is that I will give the concept which you can use in those questions and try to solve the numericals. Numericals are just based on one liner formula, but from where these formula are coming, that is what I will be discussing today. Okay, just give me a moment. I will. So this uh, one of the prime thing of this assignment 6 or the week 6 is about the internal gravity waves. So internal gravity waves is generally based on it is actually valid over a stable atmosphere. Okay, stably stratified atmosphere, which we say the term stable atmosphere. So the question immediately comes: what do you mean by stability? What do you mean by the stability? And what are the parameters to quantify the stability? Okay, so these are the couple of things which is very, very important. Okay, so let me give the title heading as the internal gravity waves. Internal gravity waves. Okay, so internal gravity waves exist first of all in a stably stratified atmosphere. Okay, and here the restoring force is actually buoyancy. Now, what is the buoyancy? Okay, we know what is buoyancy. Those who are from the physics background, we all know physics, fluid mechanics, everyone knows that what is buoyancy. But let us see in terms of atmospheric physics how we can uh, quantify the buoyancy, particularly which we call as the Brunt-Väisälä frequency. We will see all these things. Okay, but let me start with a very simple thing which we have discussed earlier also. That is potential temperature. Potential temperature. Okay, potential temperature is denoted as theta. Okay, and what is the definition of potential temperature? It's simple. Theta is equal to T P naught, a reference pressure, because since it is a potential, just like we define potential energy, and when we calculate potential energy, we take a reference that H of Z is equal to zero level. Then we calculate what is the height, and then G times that height is the potential energy of that particular body. Okay. Similarly, this is the reference pressure. This is some arbitrary pressure to the power R by Cp. Generally, this R is the dry gas constant. Cp is also the dry specific heat at constant pressure. Okay, so these are all dry. So R by Cp, this is about 0.87. Okay, so just a minute, let me. So R has a value of 287 and Cp has a value of 1005. So, oh, I'm sorry, this is not 0.87. This is about 0.287. Okay, just remember this. Okay, so this is done. This is the temperature, as you know. P naught is generally taken as the reference pressure, taken as 1000 millibar or 1000 hectopascal. Millibar and hectopascal are same. Why 1000 millibar? Because we generally say that the surface of the Earth is at constant surface pressure is 1000 hectopascal. Remember, surface pressure may change from place to place based on the elevation, based on uh, the heating and all those things. Surface pressure may change, but we take a reference as 1000 hectopascals. Okay, this is one of the things. Next is P. P is different pressure level. So as you go up, top of the atmosphere, the pressure decreases. We know this. Okay, as we go up, the pressure decreases. Okay, pressure increases as you go down. Okay, so this is one of the case. So this is the potential temperature definition. Okay, now let us do some mathematics. Take log on both sides. So this becomes log of theta. This becomes log of T. This becomes R by Cp log of P naught minus R by Cp log of P. Okay. Let us differentiate both sides. Differentiate with respect to height z. So it will be d dz of log of theta d dz d dz of log of t. This is a constant, right? P naught is 1000 millibar. I have fixed it. R and Cp, I have told you that this is a constant. So if you take a derivative with respect to z, it is not varied. So it is 0 minus R by Cp d dz, of course, of log of p. So what is this? This is 1 by theta d theta dz. What is this? This is 1 by t dt dz. And this is minus r by cp p dp dz. Apply the hydrostatic approximation, and what does that say? The hydrostatic approximation says that the pressure gradient force at the vertical direction is equal to the density. Density times, sorry, is equal to the gravity. So this becomes minus density times g. Okay. So what we next do is that we multiply with temperature both sides. So we have T by theta, d theta dz. If you multiply T here, it will be only dt dz. Minus minus becomes plus R P by P Cp rho G. Remember, from ideal gas law, rho is what? P by RT, correct? So it's R, P, P and rho cancels. So what you get finally? dt dz plus G by Cp. This is equal to T by theta d theta dz. So what we are getting here is that the change in potential temperature with respect to height is related to this. Okay. Now we define lapse rate. Okay. Lapse rate is equal to the rate of decrease of temperature with height. Okay. Rate of decrease, remember. So gamma is minus dt dz. And this term G by Cp is nothing but gamma d G by Cp. This is dry adiabatic lapse rate. Okay, this is dry adiabatic lapse. So your T by theta d theta dz can be further written as gamma d minus gamma. Remember, this dry adiabatic lapse rate is only for the parcel. So it can be considered as lapse rate of the parcel, and this is the lapse rate of the environment. Fine? Because it is in general BTDZ. So what does that mean? Now, if certain conditions exist, one, gamma D is greater than gamma. What is happening here? You have Z and you have temperature. Okay? So gamma D. Okay, let us say the temperature lapse rate is this, because gamma D or gamma, they are all generally rate of decrease of temperature. So that's why I have decreased it with height. Temperature decreases with height. This one is, let's say, gamma for the environment. Now if gamma D is greater than gamma, then what will happen? If gamma D is greater than gamma, means the rate of decrease of temperature is much more. That means this, there is more decrease of temperature. It's just like a slope kind of a thing, right? So this is a more slope and this is a less slope, as you can see. So this becomes your gamma D. Then what is happening? At some level, this, suppose at say 5 kilometers above the surface, you can see that parcel temperature is this, T of P. But environment's temperature is this. So what is happening? Your parcel temperature becomes less than that of the environment temperature. That means what? Parcel temperature, if it is less, then it will be more dense, because as you know from ideal gas law, rho is inversely proportional to temperature, right? So in an environment, if a parcel temperature is less than the environment temperature, it should fall. Right? So if gamma d is greater than gamma, or your d theta dz is greater than 0, that means it is a stable atmosphere. Why stable atmosphere? That means if you lift a parcel, if you just lift a parcel upward, it will come down. That means, remember the term of stability in electrostatics or wherever in the physics. You have a reference point. You have lifted anything in a particular direction, it will come back. If it comes back, then it is a stable system. If it does not come back and goes, it is an unstable system. Same applies here. Okay. So if you throw a parcel upward or wherever, if you see that your parcel's temperature is less than that of the environment, it becomes more dense. It comes back. Hence, it is a stable atmosphere. If d theta dz is now less than 0, that means what? Your gamma d, gamma of the parcel, is less than the gamma of the environment. In that case, temperature parcel will be more. And in that case, so in this case, your Tp will be greater than temperature of the environment. In that case, the parcel will rise because of the less dense, uh, because of the lower density of the parcel. So this becomes unstable. And when these two conditions becomes equal to 0, it becomes a neutral. It will stay on its own. There is no problem. So remember this, how the potential temperature varying with height gives you an interpretation of the atmospheric stability. Okay, so this is the main thing. Fine. Okay, so this is one of the important things. Now we will connect this d theta dz or 1 by theta d theta dz with another important parameter, which we call as the Brunt-Väisälä frequency. We will see that. Okay. So now what we will do is that let us consider a parcel. Okay. Let us consider a parcel, air parcel, and environment. This is the pure atmospheric thermodynamical part. Okay. So there is a parcel and there is an environment. The parcel is always separated from the environment. Parcel and environment are the two different entities. Okay. Number one. Number two is that, so I am writing number two as number one here, that at any level, level means at any height. Okay. At any height, pressure of parcel must be same as the pressure of the environment. This has to be true. Okay, this is the assumption of the partial theory assumption. Okay, this is one of the assumptions. Second is that environment is at hydrostatic equilibrium. Okay, hydrostatic equilibrium. Okay, so environment is always at hydrostatic equilibrium. That means at environment you can say that your vertical pressure gradient force is exactly balances the gravity. There is no disturbance. That means, right? So let me say, suppose this is your momentum equation. Remember, dw dt is equal to the vertical pressure gradient acceleration minus gravity. All other terms, let us forget for the time being. The Coriolis, all those terms. When this hydrostatic approximation is valid, when dw dt is 0, that means vertical velocity or vertical acceleration is 0. So the parcel is not accelerating. We are talking about environment. So there is no acceleration there. Only balance between these two exists. That is what the second assumption of the parcel theory. Third assumption is that the parcel is adiabatic. All the processes. So parcel is considered as adiabatic. The processes which is happening in the parcel is always adiabatic. Okay, these are the couple of assumptions which we must know. Okay, so based on these assumptions, we will try to see the stability part. Okay, fine. Let's do that. So let us consider there is a level z is equal to 0. And there is another level here, which is z is equal to some delta z. All right. So here there is a parcel and there is an environment, as you can see. Okay, this parcel is lifted here. Okay, it is lifted somewhere at some pressure level P. Remember, at this, the pressure of this parcel is exactly equal to the pressure of the environment. Okay, this is very important parcel theory assumption. Okay, okay. All the knots which I am writing, P naught, I will use rho naught, theta naught, P naught. These are all for the environment. Okay, so P naught is environment pressure, and P is parcel pressure, not partial, parcel pressure. Parcel's pressure you can write. Okay, so these are the couple of things. Okay, let's try now. So for parcel, let us have vertical momentum equation. What is that? dw dt is which can be written as d dt of, see, there is a displacement delta z, right? So can we write this? This is acceleration. Time rate of change of displacement. Its time rate of change is the acceleration. This can be written. This is equal to minus 1 by rho delta p delta z minus g. This is perfect for the parcel. But for environment, we have always said that there will be an absolute hydrostatic approximation. So minus 1 by rho naught delta p naught by delta z is equal to g. Perfect. This is all right. Okay. Now, what we will say is that using second assumption of parcel theory, okay, what is that? That, oh, sorry, the first assumption. Sorry. Using the first assumption of the parcel theory, that at any height, pressure of the parcel is equal to the pressure of the environment. So, P naught must be equal to P, right? So, in equation 1, this is suppose equation 2, okay? So, put this in equation 1. So, what equation 1 becomes? d2 by dt2 put in 1 of delta z is equal to minus 1 by rho as it is delta p naught by delta z, and this is minus g as it is. Delta p naught by delta z can be written as minus rho naught g minus g. So this is from second equation, hydrostatic approximation. This one we can write this. Oh, this will be rho naught. Sorry. So rho naught by rho g minus g. This is what you are getting. So it will be rho naught minus rho divided by rho times g. All right, d2 dt2 of delta z. This is what you are getting. Remember, not rho naught is for the environment, rho is for the parcel, and this rho is also for the parcel. Perfect. Now, rho is inversely proportional to temperature according to the ideal gas law, and we know that temperature is also proportional to theta. So, rho is inversely proportional to theta, potential temperature, which we have already seen. So, what we can do it here is that, so we can, if it is a proportionality, some k times theta, so you can directly write here 1 by theta naught. Theta naught is for the environment again. This is for the parcel divided by 1 by theta for the parcel times g. We can write this now. So t2 dt2 of delta z is now, see, theta minus theta naught. I'm taking LCM and trying to do this. Perfect. This we can do. So this is for the parcel minus for the environment. for the environment times G. This is what you are getting finally. All right. So theta of parcel minus theta of environment divided by theta of environment. This is the final equation. We will do a very little Taylor series expansion after this, and we will get the result which we want. See, now here at z is equal to 0, let environment's theta is theta naught of 0, and here the environment's theta naught is theta naught delta z. Because it is environment, it will vary, but for the parcel, remember, let me write here, for adiabatic process or for dry adiabatic process, dry adiabatic process, that is for a parcel which follows adiabatic processes. Okay, for a parcel, potential temperature remains conserved. This is coming from the basic thermodynamics. Okay, so this is important for dry adiabatic process. For a parcel, potential temperature remains conserved. Okay, so now let us come here. For the parcel, this will be theta of 0 because theta is for the parcel and at 0 height. But here at P, it will be theta of delta z. But tell me, what will be the theta of delta z? So at surface, that is z is equal to 0, theta of the parcel is theta 0, theta of the environment is theta naught 0. This is for the parcel and this is for the environment. At, okay, let me write it properly. So this is z is equal to 0. Now z is equal to delta z. This is theta of delta z and this is theta naught of delta z. Tell me, for the parcel, what will be the theta of delta z? Theta of delta z will be what? It should be theta of 0. Why? Because for the parcel, it follows adiabatic process, hence the potential temperature remains conserved. Whatever it started from, it will remain. Okay, so that's why whether it starts from theta of 0, whatever the theta of 0 it has, it will have the same theta of 0 at theta here, theta of delta z. Okay, this is very important. But for the environment, what will happen? It will be theta naught of delta z can be written as first order Taylor series expansion, that is theta naught of 0 plus d theta naught by dz into delta z. Okay, this can be written as this. Perfect. Now come to this part and put those expressions. So d2 dt2 of delta z was what? Theta minus theta naught by theta naught into g, right? So just put it here. So theta of, so actually what we are trying to see is this, theta naught of delta z divided by theta naught of delta z into g. Perfect. Let's write that. Theta of delta z is what? Theta 0. Okay. Minus theta naught of delta z is what? This. So theta naught of 0 minus d theta naught by dz into delta z divided by, let's keep it theta naught of delta z into g. Again, at z is equal to 0, here, see the parcel and your environment will be of same temperature because it has started from the same point. At 0, environment and parcel are at the same temperature. After that, the parcel has conserved the theta, but environment has not. Okay, so at surface, this is important. At surface, theta of 0 is equal to theta naught of 0 because parcel has started from same environmental condition. All right. So this is one thing. So finally, we can write d2 by dt2 delta z g by theta naught as it is. So theta of 0, theta naught of 0 can be written as again theta of 0. So theta of 0 minus d theta naught dz delta z by nothing. Theta naught I have taken already. So g by theta naught, this goes minus d theta naught by dz delta z. This part is what we call as the square of Brand-Weisshaler frequency. See, now this becomes a your two order, second order differential equation. Okay, so n square is g d dz of log theta naught. So this theta naught is for the environment. You can write theta also. It is absolutely fine. Okay, so this is your square of Brunt-Weisshaler frequency. This gives again. This gives idea of stability. Why? Stability. Why? Why it gives an idea of stability? Look at this term, d dz of log theta. We have already seen that d dz of log theta plays a critical role in understanding the stability. This is right. So hence this n square also gives you an idea of the stability. So from this expression, you can clearly say that n square greater than 0 gives you a stable atmosphere. Why? Because environmental theta increases with height. This means d theta dz is greater than 0. But if n squared is less than 0, this becomes unstable. And if n squared is equal to 0, this becomes neutral. One thing to note that n square is not the frequency, n is the frequency. Okay, so Brunt-Weisshaler frequency is n. Remember, this is n. The frequency is n. Okay, but n squared gives an idea of the stability of the atmosphere. Okay, now if you put here n squared greater than 0, look, if you put n squared greater than 0, your equation becomes this plus n squared delta z, which is equal to 0. So this gives you oscillations, right? This gives you oscillations. So oscillations means what? From here, if you just lift the parcel, it will come back, again go back. So there is something like this, oscillations. So this is related to stable atmosphere. But if n square is less than 0, you will get something like this. Okay, so this gives you exponential growth and exponential decay. So growth is what is the unstable. Okay, so what we have seen so far is that Brunt-Weisshaler frequency gives an idea of stable atmosphere or the stability of the atmosphere, and we have also seen that the potential temperature increase, particularly the environmental potential temperature increase or decrease with height gives you an idea of the stability of the atmosphere. We have seen that dry adiabatic process for a parcel potential temperature remains constant. Okay, and yeah, that's all. And n square of Brunt Weisel frequency gives you the idea of stability, but n the Brunt Weisel frequency. Don't say that Brunt Weisel frequency is n square. Okay, it is n. Now, whatever I have covered right now from this part before, so from potential temperature to from here up to this, you will find all the numericals based on this in the assignment. All the numericals. Okay. So very easy. Think about it and it will be damn easy. Okay. So if you have any questions on these parts, let me know right now. Okay. Just let me know. Then I can clear it out. Then you can just solve those questions and it will be easy. The assignment 6 will be done. Okay. Because after this, there will be only a lot of derivations are there. Internal gravity waves we will discuss. And then we will see how we can go to the pressure code level. So just let me know whether up to this there is any problem or not. Okay. So if there are no questions in this part, then we can move to the internal gravity waves. So these are the basic concepts based on the assignment 6 questions can be solved. Okay. Mostly I have seen questions on n square, n related questions and uh, potential temperature based question and simple solutions. Okay. Let me, okay. That's all. I think it's nothing left here. Let me go to the internal gravity waves. It will be a big derivation, but let us see. I can skip some steps maybe in between and then let you know. Okay. And finally, the pressure coordinate system that also I will do. Let us then first derive the pressure coordinate system. That is much more better. And finally, at the last, we will do the internal gravity waves. So that will be a good part. Okay. So let me write it here with star that this part is for assignment 6 question concepts from here. Fine. Let me now go to how we can change. So this is the pressure coordinate system. Okay, this is the pressure coordinate system. Okay. So for the pressure coordinate system, what we do is that let's see the mathematics, and after that we can uh, let you know that what is actually it means. This is x y z t. We are converting it into x y p t pressure coordinates. See, the vertical coordinate has been changed. So what happens is that suppose you have this. This is the horizontal direction. You can take it as x or y, whatever. And this is z. And is suppose a variable remains constant in this path, some q which is constant. Okay, let us say the pressure here is P3, vertically upward. Here the pressure is P2, and somewhere near here, suppose the pressure is P1. The distance between these 2 points where the pressure are P1 and P3 is delta x. Okay, fine. This is what you have. And let's say this is some delta z. Okay. Now, can we write P3 minus P1 by delta x as P3 minus P2 plus P2 minus P1? Yes, we can, right? It is okay. What we'll do here is that we keep P2 minus P1 by delta x plus or minus P2 minus P3 by delta x. Okay, so P2 minus P3, I have taken a negative sign. Intentionally, I have taken a negative sign. You will understand why. So P2 minus P1 delta x minus, let me write this P2 minus P3 into delta by delta z into delta z by delta x. We can write this mathematically, at least we can, but there is a physical meaning of it also. Look, P2 minus P1 by delta x. P2 is here in the Q is equal to constant line. P1 is also there and the Q is equal to constant line. So can we write this P2 minus P1 by delta x at some constant Q line minus P2 minus P3 by delta z as it is. P2 and P3, yeah, Q is some variable which is constant. Let it be theta, potential temperature, or it will be pressure, or it will be temperature, a constant temperature line, or a constant pressure line, or a constant potential temperature line. Anything. It can be constant density line also. Any variable. Okay, any arbitrary variable. Okay. We will take Q as pressure here because we are talking about pressure volume. Okay. Hmm. We will see that. Okay. Next, see P2 and P3. This difference is happening in the vertical direction. Correct? Because this is the Z. So P2 minus P3 delta Z into I am writing this as delta Z delta X. Partial. Can write. So what is happening finally? This is of course P3 minus P1 by delta X. So this is simply we have started with the Z coordinate, right? P3 minus P1 at some Z, which is Z is equal to 0 here, doesn't matter. This is at constant Q, and this is in the vertical direction, not this one, this is at constant Q. This is in the vertical direction, so delta P delta Z and delta Z delta X. Can we write this dP dZ or delta P delta Z as minus density times G, hydrostatic approximation, right? So finally, what we are getting is that, see, left hand side delta P delta X at constant Z, right hand side delta P delta X at constant Q minus minus of rho G into delta Z delta X. Now let my Q is equal to pressure. This Q, which is an arbitrary variable, now this is pressure, a constant pressure line. Okay, so what we can write? Delta P delta X at Z will be equal to delta P delta X at constant pressure P plus rho G delta z delta x, right? So this will be also at q, constant q, okay? Because as you can see, there is one point which is at q, okay? So this is also at p. Now, at constant pressure, delta p delta x is what? Zero. At constant pressure, how can pressure vary with x? This is gone. So now, what will happen is that your delta p delta x of z is equal to rho times delta delta x of gz at p. Now, if we divide with density, what you get? Delta is gz can be written as phi. This is called the geopotential. नहीं P2 और P3 P2 और P3 P2 और P3 लेके रखे हैं नहीं P2 P3 देखो इन एक्स डायरेक्शन लिखा है बट हमने चेंज कर लिया ना इसको जेड में कर लिया इसलिए वो चेन चेन डेरिवेटिव चेन रूल यूज किया हमने ताकि वी हैव दिस थिंग अंडरस्टूड so this is finally the result what does it say see this is the pressure gradient force there is a negative sign of course so can we put yes we can put just put a negative sign here. So the pressure gradient acceleration in the z, x, y, z, t coordinate can be replaced with the gradient of geopotential at pressure coordinate. Therefore, so this is important. This is x direction. Similarly, for y direction, it will be this 1 by rho delta p delta y z will be minus delta phi by delta y at constant. Therefore, my momentum equation at x, y, p, t will be what? du dt, which can be written as delta u delta t plus u delta u delta x plus v delta u delta y plus, wait, right now let us wait here. Okay, what we generally write is delta p delta z is equal to minus 1 by rho delta p delta x plus something जो भी है whatever. Okay, now what we will do is that see vertical velocity, we are changing the vertical coordinate, right? We are changing the vertical coordinate, so we will be mostly focusing on the vertical velocity. So vertical velocity is what? W, which is written as dz dt. But in the pressure coordinate, let the vertical velocity be omega. And how we can write this omega? Simply dp dt. That's all. That is how we will be writing omega. Same as this. This is for the xy zt coordinate. This will be for the xy pt coordinate. But how this omega and w are related? Very simple. So omega is dp dt. Can I write this dp dz into dz dt? What is dp dz? Your hydrostatic approximation again comes. dz dt is what? This w, the vertical acceleration, sorry, speed, velocity. So omega is related to w by this relation. All right, this is one thing which you must know. Now let us focus on this w delta p delta z. Okay, this can be written as w delta Oh, sorry, no, delta U delta. Can I write this as delta U delta P into delta P delta Z? Yes, we can. So W delta U delta P, keep it as it is. What is this? Same, minus rho G. And minus rho G times W is what? Omega. So you understand, from vertical coordinate as Z, that is XYZ coordinate, we are converting it into XYPT coordinate. This. Therefore, momentum equation becomes this: delta U delta T plus U delta U delta X plus V delta U delta Y plus omega delta U delta P is equal to minus. Now delta phi by delta X will come instead of this. We have just now derived. Okay, this is for the Z, but this is for now P coordinate. Okay, this plus Coriolis, whatever terms you have, this is what you get. Similarly, for horizontal, sorry, the meridional momentum equation, that is V y direction, it is as simple as that. Same, delta V delta X plus V delta V delta Y, that is the same. Omega delta V delta P is equal to minus delta phi by delta Y. Instead of minus 1 by rho delta P delta Y, which we write in Z coordinate system, now we are writing delta phi by delta Y in the Y momentum equation. Okay, this is another. And how the hydrostatic approximation looks like? It's just this. So hydrostatic approximation at xy pt coordinate is simply this: delta phi by delta p is equal to 1 by rho with a negative sign. This I am not deriving, I'm just writing it right now. Okay, so these are the couple of changes which you get in the xy pt coordinate. So what is happening actually? So earlier, what we were doing is that you have a z is equal to something, some level. So z is equal to say 0 meter surface. Earlier, the momentum equation was at this surface, or some z is equal to 500 meters, 1 kilometer, like that. In that surface, somewhere there is a low pressure, there is a high pressure somewhere, and there is some changes of pressure, low, high, like this. Right? So pressure was changing in your, so this is z is equal to 0 surface. Let us say this is your y direction. Let us say this is your x direction. So that's why at z coordinate system, we were writing delta p delta x or delta p delta y as the pressure gradient force. But now what we are doing, we are converting here to something like this. Now my surface will be of constant pressure. So for z is equal to the, let us say this is p is equal to some 1000 hectopascal. Okay. Now we will have geopotential lines. Okay. These are geopotential lines. These are phi lines. Phi 1, phi 2, whatever. These are phi lines. So there will be change in the, so this is again x, this is again y. This will remain same. Only thing is that we will have delta phi delta x, delta phi delta y. Okay, this is the only change when you use the pressure, constant pressure surface. Okay, so this is one of the things. Okay, I want to show you this thing. Let me see. Using maybe just uh, see whether it works or not. So let us go here. Okay. And let's go to, yeah, this. Okay, so these are the forecast. This is uh, mean sea level pressure. That means at Z is equal to 0. Okay. How the pressure changes. See, at Z is equal to 0, you can see that there is a gradient in the pressure. See, 1004 here, then 1002, then 1000. You can see that everywhere the values are different, 1004, 1002, right? So in the X direction and in the Y direction, you can see that there are pressure gradients because it is a constant z surface. Z is equal to 0 surface. Similarly, if you go to z is equal to 500 meters, there also you will see this kind of pressure gradient. That's why in the horizontal momentum equation, we have used delta P delta X or delta P delta Y. Okay, remember this? Okay, now I will change the chart and you will understand. See this. This is at 500 hectopascal. So 500 hectopascals means it's a constant pressure surface. Okay, whose height is average height is about 5,000 meters. And you can see these are the geopotential height. See 592. You just multiply by gravity. We have written GZ, right? So thus multiply by 10, you will get the height or the geopotential height. This is the geopotential. I'm sorry, this is not the geopotential, this is the geopotential height. But if you multiply by G, that becomes the geopotential. So these are the delta phi delta x. See, there is a gradient in phi. Delta phi delta x, delta phi delta y, etc. Understood? So this is a constant pressure surface. Just now what we have derived. Here you will find that there is a variation in the phi geopotential. This 576, 588, these are geopotential height. Okay, so these are the geopotential height. Fine. This is what I wanted to show you. All right. So this is the difference between the XYZ coordinate and XYPT coordinate. All right. So fine. Any question on this? If not, they can move. Okay. So, so this is a simple pressure coordinate conversion. Now let's go for. We have enough time. We can go for a long derivation. Okay. So let me start the actual internal gravity waves. Its derivation, as you know, will depend on this perturbation technique. Okay, so this is internal gravity waves. These are also called as the buoyancy waves. Okay, this is also called as buoyancy waves, and because this is the restoring force. This is the restoring force, and it exists. I have written it already, but I am writing it again. When atmosphere is stably stratified, that means your density generally decreases with height, or yeah. So that is the case. The parcel density should be higher than that of the environment. So these are the couple of things. So in the atmosphere, gravity waves can travel in both horizontal and vertical. Okay, but in case of oceans, in general gravity waves travels vertically. This internal gravity waves, remember. Sorry, not vertically, horizontally. Why? Because in the vertical direction, there is a boundary, right? In the vertical direction, there is a boundary. So that creates standing wave pattern. Okay, there is a so this is the ocean in the atmosphere acts as a boundary, and there is a surface of the ocean. Surface of the ocean is the depth, the last layer of the ocean that is acting as a boundary. So the wave will be like this to create a standing wave pattern. These are a couple of things. Okay, one of the assumptions of this is that we will neglect Fourier force. Okay, this is one of the assumptions, and we are taking XZ plane. We are not taking the Y axis. Too many axes will complicate the process, so we will not take that. Okay, and this is one. This is second. Third is we will take one approximation called Business approximation, which says that rho is constant vertical. Okay, so this is the assumption. These are the three assumptions which we will be taking. So what we will do is that, okay, we have already seen the pressure coordinate conversion, but right now we will again come back to only x, y, z, t. We are not going to the pressure coordinate. Okay, just for simplicity, we are doing this. Okay, so what are the steps for any derivation of dispersion relationship of any waves? What we have done so far in the last session also is that we write down all the equations which we have in the xz plane because we are taking them. So first is the horizontal momentum equation. So delta u delta t plus u delta x plus w delta u delta z because v is not there. Y I am not considering plus 1 by rho delta p delta x. Coriolis term we have neglected. Delta w delta t is the z momentum equation because z plane also we have. So u delta w by delta x plus w delta w by delta z plus 1 by rho delta p delta z plus g. G will be always there in the vertical momentum equation. Next, continuity equation, mass conservation. Thus, delta w delta z is equal to 0. We are using compressible fluid. Sorry, incompressible fluid, which is not a good assumption for your air because atmosphere consists of air which can be compressed, right? But we are taking an approximation which is very crude, but still this is for a simple derivation. That's all. And finally, the energy equation, thermodynamic equation in terms of theta. You will see that here we will be using the Brand vessel frequency at the final expression. Okay, where theta I have already defined, which is conserved for dry adiabatic process for the parcels. P naught is the reference, which we generally take at 1000 MB, and this R by Cp is 0.287. We have just now shown that. Okay, this is conserved. Remember. Okay, take again log of theta, so it becomes just a minute. Let me write this expression properly. So theta is equal to 1 by rho r, and this will be P naught r by Cp. Okay, and you have 1 upon P r by Cp minus 1. Okay, and we have done this in the last session also. So this will be r minus Cp by Cp. This becomes Cv by Cp because Cp minus Cv is r, and the ratio of Cp by Cv is gamma. So we are writing 1 by gamma. Cp by Cv is gamma, remember. Okay, so finally we are getting P naught on r by Cp divided by rho r and 1 upon P 1 by gamma. Okay, fine. I think, oh, okay. Sorry, this is nice. Okay, so this we can get P to the power 1 by gamma divided by rho and some constant. Okay, so now take log of theta, that is equal to 1 by gamma log of P minus log of rho plus log of K. Okay, now write the perturbation. Perturbations, what are those? Density rho is rho naught, which is constant with height, plus rho dash, which is bearing x, z. Okay. Next, P, I'm not writing all those things. P bar, which is a function of z. Rho is a constant with z because we have taken Boussinesq approximation. But P is varies. Okay. Theta also varies with z plus theta dash. U is equal to U bar. Again, this is also, we are assuming constant with z. These are all our choices, okay? So you can change it, but it will become much more complicated. That's why we don't take it. W again, we are taking only the perturbation. W bar is 0. These are all our choice. We can take it to make everything simplified. Fine. So these are the things. And now let's do another thing. 1 by rho delta P delta Z plus G. This is the part of the vertical momentum equation. We will write the perturbation terms. So this is rho naught plus rho dash, sorry, rho dash, delta delta z of p bar plus p dash plus g. Can we write this as the rho naught 1 plus rho dash by rho naught, okay, delta p bar by delta z plus delta p dash by delta z plus g. Yes, we will have binomial expansion, and hence we can write this as 1 by rho naught 1 plus rho dash by rho naught to the power minus 1 delta p bar by delta z plus delta p dash by delta z plus, using binomial expansion and neglecting higher order terms, we can easily write this as minus rho dash by rho naught. The same thing repeats. All right. So what you get is 1 by rho naught delta p bar by delta z plus 1 by rho naught delta p dash by delta z minus rho dash by rho naught delta p bar by delta z and minus rho dash by, sorry, this is rho naught square delta p dash by delta z plus product of the perturbation term is 0, so we can neglect that. What about delta p bar by delta z is nothing but minus rho naught g because this is a mean thing, and mean in the mean condition, hydrostatic assumption is valid. So this and this can be chopped out. So finally, what we are getting? We are getting 1 by rho naught delta p dash by delta z minus rho dash by rho naught square into minus rho naught g. This term. So you getting rho naught delta p dash delta z plus rho dash by rho naught into g. Look how the perturbation equation looks like this. Okay, so this is the hydrostatic part of the momentum equation, which looks like something like this. Okay, so just remember this. So what we have done so far is this: 1 by rho delta p delta z plus g. When you have the perturbation terms, we get reduced into this. Okay, now let's go back to this equation. Which one? This one. And apply. So theta is equal to what? Theta bar plus theta dash, which is a function of z. This is a function of z. So log of theta bar can be written as 1 by gamma log of p bar minus log of rho naught plus log of k, the constant which we have. Because this base state should follow the actual equation, which is followed. Perturbation will also follow. So we are writing this plus p dash minus log of rho naught plus rho dash and log of k does just remains like this. All right. Now, if important thing is that I am taking this. Okay, this is equal to 1 by gamma log of. In the same way, we will do it here. Minus log of rho naught. All right, and log of t. Important thing is that log of AB, we know that it is log A plus and log of 1 plus epsilon is nearly equal to epsilon if epsilon is much smaller than 1. Here, perturbation is much smaller than the theta bar or 1. So, we can write this expression as log of theta bar plus theta dash by theta bar is equal to 1 upon gamma log of p bar plus 1 by gamma p dash by p bar plus, sorry, minus log of rho naught minus rho dash by rho naught and log of. So remember this equation. See, this is valid, so you can swap this out. Finally, what you get? Theta dash by theta bar is roughly equal to 1 by gamma p dash by p bar minus rho dash by rho. This is what you finally get. Okay. Now, here, what we will do is that this rho dash is equal to p dash by cs square minus rho naught theta dash by theta bar. Why I am writing this cs square? Because this cs is the acoustic wave speed, which is very large. Okay, so cs square is very large. Hence, this term can be neglected. So rho dash by rho naught becomes roughly equal to minus theta dash by theta bar. Remember this, we will be using this. Okay, so now what we can write is that the momentum equation can be written in terms of perturbation path. This we have done lot many times in the last couple of sessions, so it is easy for you to now understand. This is 1 by rho naught delta p dash delta x, put that equal to 0. The next equation becomes del del t plus u bar del del x of w dash plus 1 by rho naught delta p dash by delta z minus, instead of rho dash by rho naught, we are writing this. Put that equal to 0. So what we are writing is that this case we were having this this thing. This thing rho dash by rho naught is now replaced by theta dash by theta bar. That's all. That is the only change. What we will do is that we will operate minus del del z of this and del del x of this. Okay. So also we have continuity equation which can be written like this. Put that equal to 0. And we have the thermodynamic equation which is like this. Okay. For adiabatic. Okay. So once we do this, use this operation, and so this is, let's say, A, B. So take delta delta x of B minus delta delta z of B. So once you do this, I will write the final expression del del t plus u bar del del x. You will get delta w dash by delta x minus delta u dash by delta z and minus g by theta bar delta theta dash by delta x equal to 0. All right. What else we can do? So what we do is that we take again. So this is, suppose you, okay, let's write all those equations. So this is E, this is B. Okay. So let this be some E. Take del del x of E. So you get del del t plus u bar del del x of delta square w dash by delta x square minus delta square u dash by delta x delta z minus g by theta bar. These are all constants or not dependent on x. So this becomes 0. This becomes f. All right. Now look at this delta u dash by delta z. Can it be written? Sorry, delta u dash by delta x. This part can it be written as delta w dash by delta z? So delta u dash by delta x can be written as minus delta w dash by delta z. Put that in this, and we finally get u bar del del x plus delta square w dash by delta z minus g by theta bar, whatever it is, just keep it as it is. So this becomes now the g. Now operate del del t plus u bar del del x on g. When you do that, it's simply this del del t plus u bar del del x whole square You have this delta square W dash by delta x square, delta square W dash by delta z square. Done. Next, minus g by theta bar del square del x square, and you have the operation again because every term you have to operate. This is theta dash, put that equal to 0. This becomes your H equation, right? We are now almost there. Okay, so just a couple of things. So you have del del t again. So repetition, you have to write this, otherwise it will be difficult for you to understand. Plus theta bar. Okay, and you have, see, del del t u bar del x of theta. Can we have this expression? Yes. See this. This is nothing but, so from D you can write. So you can directly write this del square del x square minus w dash d theta bar by dz. Okay, put that equal to 0. This comes from D. Okay, now further you can just solve u bar del del x whole square del square w dash by del x square del square w dash del del square. I think this is very bad expression, but this is to be done like this one. So we have already got the final expression. Look at this. This is nothing but what? The Brand-Weissala frequency square. Okay. So we are very close to our final expression of the wave equation. And you have del square W dash by del x square plus del square W dash by del z square plus n square x square equal to 0. So this will be the ith equation, and this is the necessary wave equation. And this is mostly in W dash. So we can explain that this is nothing but A to the power iota kx plus mz. Remember, this is a 2D wave minus omega t. So this is the assumption. Assume the solution like this. Okay. Similarly, you can do many other things like u dash can be written something like this. Okay. So I'm not writing this. So finally, when you put all these things and do a couple of steps, you will get the equation as something like this: k square plus m square. So put w dash on I and solve. Okay, there are a couple of steps which I have skipped here. You get omega minus u bar k whole square minus k square n square is equal to 0. So omega minus u bar k whole square becomes equal to n square k square divided by k square plus n square. This is called the intrinsic frequency. Okay, so this new hat becomes plus minus nk root over k square plus n square. And you can clearly see that your omega is dependent on k or group or the phase velocity is omega by k, which is nothing but plus minus n divided by k square plus n square to the power half. So these are dispersive waves. Okay, these are dispersive waves, and this is the phase velocity. Let me write it. Okay, and this is the dispersion relation. Okay, this is the phase velocity. Then we have the group velocity, which is nothing but Cg, which is delta omega by delta k. So just do the derivation of this. That's all. When you do that, so Cgx, the x component group velocity is delta omega delta k. Okay, and Cgz delta omega delta m. This comes out to is nm square divided by k square plus m square to the power 3 by 2. Similarly, Cgz delta omega by delta m, which is, let me see what the expression is, minus nkm divided by k square plus m square to the power 3 by 2. Now, we will assume one thing. Let k is greater than 0 and m is less than 0. See, these are the, so k vector is the propagation vector. So wave will propagation in this direction. Okay, so wave travels along k hat direction. Okay, so this is what you have. So k vector is equal to ki hat plus m k hat. K hat means the z hat. Okay, let me write like this. But remember, here m is negative. So now, if we have to make a diagram of all, let's do that. This is very interesting diagram. You'll understand. Okay, so this is your x, this is your z. All right. Now we can make some phases of the wave, just like this. These are the different phases. Okay. So what you can see, k is greater than 0, m is less than 0. So m, which is the z direction, is less than 0, means negative. So something like this, and k is positive. So the wave propagation will be happening in this direction. Okay, so the wave is propagating like this. Okay, so these brown color lines are the phases, and this is the wave propagation direction. So wave is propagating, the phase of the waves are propagating in this direction, because we have chosen k is equal k is greater than 0, m is less than 0. Okay, this is the wave propagation direction. So let me quickly do this wave propagation. All right, what about your phase velocity? Okay, it is a phase speed, no problem. What about the group velocity? Group velocity, if we assume this p greater than 0, m less than 0, cgx becomes what? This is m square, so it is positive. So cgx will be positive. What about this? M is less than 0, k is greater than 0, so this becomes negative, positive. Both are positive. So your group velocity will be in the along the phase. but in the positive x direction and positive z direction. So this is the direction of the group velocity. Because pgx is positive, pgz is also positive. So group velocity at each of the phases will be along the phase and in the positive direction. This is the direction of the group velocity. I will write it down. So cgx is positive, cgz is also positive based on these conditions. So this is group velocity. All right. Next is what? Let's see what happens to the u, the velocity perturbation. Okay, zonal velocity perturbation. And what about w? Okay, so let's go to the beginning. Let's come here. Okay, yeah, let's come here. That is fine. So what we can say is that suppose let me do one more thing. Suppose mm, let us have this as low, this as high, this as low, this as high, low, and high. So low means your P dash is less than 0, perturbation. So P dash is greater than 0, P dash is less than 0, P dash is greater than 0, and like that, like that. Okay. This I am making it. Okay. This is the case. If this is the case, let's go now to the this equation. The very first equation. This P dash is positive. So this part, okay. So actually what we are doing is that we are all writing this u dash as some u naught e to the power iota kx plus mz minus omega. Similarly, b dash, sorry, w dash. Similarly, p dash, everything we are writing like that. Okay. So what we can do is that this equation, this equation, let me write it here to understand what I'm doing. Is that del t plus u bar del x of u dash plus 1 by rho naught delta p dash by delta x. So if we assume if u dash is equal to some u cap e to the power iota kx plus mz minus omega t, and similarly w dash is w hat e to the power iota, the same thing, p dash p hat e to the power iota, same thing. Okay. So if we just put it here, can we write this expression as this? Minus iota omega plus u bar iota k u dash or u hat, I will say, plus iota k p hat. So p hat divided by u naught, that is equal to 0. All right. So what will happen here is that we can write omega minus u bar k u hat is equal to k p hat. So if p hat is positive, that is p dash is positive. So if p dash is positive, which is the high pressure region, p hat will be also positive because this does not change the sign. The amplitude will be positive, or then if p hat is positive, then u hat is also greater than 0. So wherever p hat is positive, u hat is also positive. Also, we have the continuity equation. Remember, this plus this equal to 0. So what we can write? Iota k u hat is equal to minus iota m w hat. So U hat, if it is positive, W hat must be negative. They have opposite sign, remember. So what will happen finally is that now if we have to write the U hat or have to do the U hat, so what will we do? Okay, remember W dash is positive. Is it true? No. See, iota iota cancels, but M we have assumed negative. So if M is negative, there is a minus sign. So W hat is also positive. Okay, there is a negative sign, but M is also negative. Negative, negative, positive. So within the phrase, this is the direction of. So U hat is positive, W hat is positive. That's why it is going like this. This is high, but for low it will be negative. All will be negative. So like this, right? Like this. U hat is negative. This is negative. Understood? So this is how the velocities will travel. Velocity perturbation will travel. Okay. So this is how the velocity perturbation will happen. We can do many things about the temperature also, but let us not do that. So this is how the internal gravity waves will look like when you have a condition where k is greater than 0, m is less than 0. Look at this. Your energy is traveling upward, going more towards the z direction, higher altitudes. How we do now know that? The group velocity is traveling towards the positive z. So this group velocity generally carries the energy far away to the stratosphere and mesosphere, and it significantly affects the mesosphere temperature. Okay, so that is what assignment 5 question was. So with this, I think I can end today's talk. It's a bit clumsy, a very big derivation, but ultimately, from the whatever mathematics we have got, this is what the picture tells you. Okay, just try to see if you have any doubt. You can ask me in the next session. Okay, with this I will end. So this is the complete picture of the internal gravity. Okay, so the next session I think we have assignment 6 questions, of course. With that, we have natural coordinates and all those things are there. So we will look into that. Okay, a bit mathematical. Let's try to look into it. Will be good. Okay. So we have seen so many things today. Okay. So let us then stop. If there is no question, then we can. Okay. Okay. All the best.